In this video, we're looking at graphing motion. So we're going to talk about a whole range of ways that we can represent moving objects and how we can interpret data from those graphs. So an intro question just before we get started. If I'm traveling at a constant speed of 30 meters per second, what is my acceleration? Then think about, what does a negative velocity mean? And what is my acceleration if I go around a roundabout at constant speed? So pause the video for a second, think about what those answers are, and then continue. Hopefully you said that if you're traveling at a constant speed, your acceleration is 0, because you're not speeding up or slowing down. Constant speed means you're not changing your motion. If you're not changing your motion, you can't be accelerating. A negative velocity just implies the opposite direction. So it doesn't matter which way we define, but the result of the negative is either the opposite. So it could be down, it could be to the left if we use our general convention, but it could be anything else depending on what you've defined as positive. And the acceleration as I go around a roundabout, well, because I'm changing direction and therefore I'm changing my velocity, I must be accelerating. Because remember, acceleration is the change in velocity over the change in time. So it doesn't have to be a change in speed. That would give you an acceleration, but it can also just be a change of direction. So technically, if you change direction, if you turn, go around a roundabout, etc., you are then accelerating. Okay, so the learning outcomes for today are using the graphical methods to represent linear motion, including constructing a graph that shows position time, velocity time, and acceleration time. You're also expected to use these representations to determine things such as the position, the displacement, the distance, the velocity, and the acceleration from these graphs. You can use these techniques to calculate an instantaneous velocity and an instantaneous acceleration of an object, and you can use a position versus time graph to construct a velocity versus time graph. Subsequently, you can use a velocity and time graph to then construct an acceleration time graph. Okay, so let's get into it. So this graph here shows the position of an object. We often refer to it as a body in physics. It's the position of a thing, a body, over a time interval. And remember, in one dimension, distance and displacement are the same, because if you travel in a straight line left to right, the distance you've traveled and the displacement from your starting point are exactly the same. So we often can interchange for stage 1, because we really only talk about one-dimensional cases for most motion. The origin of this graph is where it originally was at time equals 0. So it could have still been moving, we don't know, but at time 0 it was at the origin. So it was at, let's call it a home or something like that. In this case, the displacement, the distance that you traveled, can be found by just directly reading off the graph at whatever time interval you want. So if we look at 6 seconds, we go up, we traveled 3 meters. So it is a displacement, so we would say it's 3 meters, say to the right, because it's a positive value. So 3 meters to the right of the origin, and that is our displacement at time equals 6 seconds. Now if we look at velocity, given that velocity is distance divided by time, or displacement divided by time to be more specific, the graph is plotting a distance, or a displacement if you will, over a time. So if we think about the slope of the graph, the rise over the run, that gives us distance over time. And that is what the velocity is. So a steeper line gives us a steeper slope. That implies that we're covering a distance in a shorter period of time, so we must be moving faster. Consequently, a much smoother slope means it's taking a very long amount of time just to cover a short distance, so we're moving very slowly. In physics, we sometimes refer to this as the y2 take y1, just like you would see in maths. This is the slope formula. But often we use the final take initial concept, and that's where the delta comes in. So we often just call it delta t, delta s, things like that. That's just the final take initial, or y2 take y1. So if we look at the standard slope formula from maths, we've got the y2 take y1, where did we finish in the distance, minus where we started, and x2 take x1 we substitute for time, the difference in time over that interval. So the slope gives us our velocity. So mathematically, we can use distance time graphs to calculate velocity by finding the slope. So now in this question, I want you to have a go at answering these. So you've got a motion that's graphed by a distance time, or a displacement time if you will. It's asking to describe the motion, state the total distance, calculate the average speed. So if the time runs out and you're still going, just pause the video, but otherwise have a crack at it. Okay, so part A is saying to describe the motion. It's traveling at constant speed originally, traveled 20 meters in 5 seconds. It then remains stationary for 5 seconds and then travels at a higher constant speed. So if you think about this, the distance that it is covering over a period of time is the same for every interval. So if we blew this up and made it really big, in 1 second it would travel 1 meter. In the next second it would travel another meter. So on and so forth. Obviously it doesn't because it's in 5, but if we divided it out, we can see that it's increasing by the same distance at the same time intervals. So that straight line is constant speed. Then at this point from 5 seconds, it's 20 meters from home. A second later, it's still 20 meters from home, still 20 meters from home. So that tells us that it's not moving. And then it takes off again, and much steeper slope, so it's covering a bigger distance in a shorter period of time, means it's traveling faster. Then the total distance traveled, 30 meters. Remember, the distance is just given to us, so we just look at where you finished and the distance you traveled, and it's 30 meters. The average speed, so average speed is just the total distance divided by the total time. We get 30 meters, it took us 13 seconds, 2.3 meters per second is the velocity. Make sure that you use the right number of sig figs. Technically that would be a placeholder as well. So here are some examples of the different motion graphs. We've got distance time, velocity time, acceleration time, and we're going to go through the next two very, very shortly. But we can see here distance time, if we have the flat line, is stationary motion. A straight line on a slope for distance time is constant speed. If it was curving up, it means we're increasing speed, so we're accelerating. And in this case, if we're curving down, we're slowing down, so we're decelerating, so we're decreasing the speed. Now let's look at velocity time graphs. So the motion of an object can also be described by a velocity time graph. We've seen the distance time is how far you get from your home in a certain period of time. And now we're going to look at how fast you're moving at a certain period of time, your velocity. So we've got a graph here, a velocity graph. We can see that at time 0, we're moving at 4 meters per second. We continue to move at 4 meters per second for 2 seconds. And then our speed, our velocity, is decreasing over the next time interval. So if we want displacement or distance, given that velocity is the distance divided by time, if I rearrange this formula, it gives me how far I've traveled from my displacement as velocity times time. So if we consider how far we traveled in the first 2 seconds, so 2 seconds, I'm here, I've moved at 4 meters per second for 2 seconds, so my displacement is 8 meters to the right or up, depending on what we're defining. But you may notice that this is also just the area under the curve. So if I say 4 meters and 2 meters, if I multiply these, I get this area, and it gives me the same value. So if we calculate the area under the curve of a velocity time graph, we get the displacement. Remember we talked about previously the slope of a distance time graph gives us velocity. Now we've got a velocity time graph. If we calculate the area under it, we go backwards and we find the displacement. If we have an example like this where we go up, down, now we've crossed through the x-axis and we've gone into the negative values. If we calculate an area above the time axis here, this is a positive displacement. So this is moving away from home. for example, or away from the origin, whatever you're defining. Anything that's below the axis, like this point down here, represents a negative displacement because we're going to have a negative area. You do the same concept. You do the area, which will be -8, so it's half base times height, but you're going to have a negative value. So if we want to find the total distance traveled, you would subtract the positive, the time or the distance that you've traveled away from home, but then for this interval you've started heading back towards home, so you would subtract that from it. There's a couple of different forms that you'll see. You may see a graph like this. You're not going to see curved examples. You're not expected to calculate the area under a curve. That's some complex integration. But things like the right angle triangle is the half base times height. A rectangle is pretty straightforward, length times width or base times height again. A trapezium, so we could knock this formula out as a trapezium. If you forget the trapezium formula, it's not on the formula sheet, that's completely fine. Just split it into a triangle, and a rectangle, and you get the trapezium anyway. So it's just skipping a step if you know how to do that. So now we've got a velocity time graph, and they're saying, how far did this object travel in 10 seconds? So we know with the speed we were moving, we came back, and remember, when I say we came back, this is not actually changing direction. We're still a positive velocity, so we're slowing down. At this point, our velocity is 0, and then it starts traveling in the negative direction. So this is moving backwards, this is slowing down, this is speeding up away from whatever the origin was. So if we calculate the area under the curve, like I said before, we get this change in velocity times the change in time, and we get 100 meters as a total. So because we're just talking about the first 10 seconds up to this point, so we've just done our half base times height, 20 times 10, we get 100 meters in the first interval. Between 10 and 15 seconds, as I mentioned, we're heading back towards our origin point. So we've got to 0, the velocity of 0. Now we're in negative velocity, so that means we're heading back the other direction. At this point, we don't stop. We still have a negative velocity, but it's now going back towards 0, so we're slowing down again. So we're speeding up away from the direction we're traveling, so we're speeding up home, and then we're slowing down, still traveling in the direction to home. Just like we saw before, the velocity can be found from the slope of a distance time graph. Acceleration is also the slope of a velocity time graph. So we're sort of seeing a pattern here. The slope gives us kind of the next step down, if you will. So if we think of it going from distance or displacement, velocity, acceleration, if we have distance time when we get the slope, we get velocity. Now we're about to see that if we get velocity time graph and we do the slope, we get the next step down, which is acceleration. And the reason for it is because of the same concept of the formula. Acceleration is just the change in velocity over the change in time. And we sometimes write that as v2 take v1, or as per like the SACE formula sheet, and what we'll mainly use, you'll see v minus v naught. So that's the same as the rise over the run. The change in velocity is the change in y, and the change in time is the change in x. So rise over run. So that's where we get the slope from. So an example, just like in this question, we get rise over run or delta y over delta x, depending on whatever you want to call it. In this case, that gives us acceleration. So we find from this graph that our acceleration is 0.25 meters per second squared. Here we can see a couple of examples of velocity time graphs. So you can see here we've got a straight line. This tells us that we've got constant acceleration because our velocity is increasing at a steady rate. It's a straight line. So the amount that it increases here and here and here are all the same. So constant acceleration. Here we still have a straight line. So it's still constant acceleration, but it's steeper. So we have a larger acceleration, but the change is still constant, or the change is 0 is probably a better way to say that. Now in this one we've got a horizontal line, velocity is 5, a second later it's still 5, still 5, still 5. So this is constant velocity, and remember if the velocity does not change, therefore the acceleration must be 0. In this example the velocity is decreasing, you can see we start at 10 and we finish at 0, and it's a straight line again, so it's changing downwards, it's slowing down by a constant amount. So this is constant deceleration. These two graphs here show us some curved examples. So it's increasing by an increasing amount. So this would be an increasing acceleration. The velocity is getting faster and faster and faster, but not at a constant speed. And in this case, we're decreasing the acceleration. So we start off, we're speeding up, speeding up, speeding up, and then we're still increasing speed, but not by as much. So the acceleration is slowing down or decreasing. Like I said, you won't be given these kind of questions to explain. You would be expected to draw this. If I gave you an example, I said, show me what an increasing acceleration would look like on a velocity time graph, but you're not expected to calculate slopes or areas under these kind of curves. So a quick summary for this is that if we have a negative area, it just represents the opposite direction. So just like when we said negative velocity and negative acceleration is the opposite direction, a negative area of a curve under the curve just gives us the opposite direction. So we would subtract that if we wanted a distance or something like that. The slope gives you the value above it. So if we had velocity time and we take the slope, we get acceleration. If we had distance time and we take the slope, we get the velocity. The area under the graph gives you the value below it. So in this case, I've flipped it and I've tiered it as acceleration is the top, then we go velocity, then we go distance. If I want to go up, I take the slope. If I want to go down, I take the area under the curve. And if you forget this, you can just write out what the formula is. So if I write the formula for acceleration, it's the change in velocity over the change in time. I look at my graph and I go, oh, sweet, I've got velocity and I've got time. I just need to figure out, is this a slope question or is this an area under the curve question based on that formula? So some more summary questions for you. As before, you'll have a minute. If you need any more time, just pause the video, but give these questions a crack.
Nothing's gonna stop me. Hey, yeah. Nothing's gonna stop me. Feeling so right. Nothing's gonna stop me. Hey, yeah. Nothing's gonna stop me. Feeling so, 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 feeling
Alright, so let's have a look at this. So determine the distance moved by the body, total area under the graph. So here we've got the 20 times 10. We divide it by 2 because we're just using triangle formula. And here we've got the 5 times 8 divided by 2. So the trap here that you may be thinking is, why didn't we subtract this? But that's because they've asked for the total distance moved, not the displacement. So because remember, this is heading back towards the origin. This is still a distance, but if I wanted the displacement, as I do here, I would subtract it to find out how far from my starting point did I end up. Average speed is just the total distance divided by the total time. So if you got this question wrong, it obviously would have affected this answer, but that's okay. In physics, if you get part A wrong, but you do part A completely right, but use a wrong value, you'll still get your marks for it, because that's not assessing the physics, that's just assessing your ability to use a value from a previous question. Final displacement, now we subtract it. So we take the area above that we did here, and we subtract the area below, and we get 80 meters. So we moved 80 meters to the right, or in a forward direction, or up, whatever you define that as. Average velocity is the distance divided by time. So we take our total distance from before, the displacement, this time, and we divide it by the time. So we get 5.3 meters per second. And again, we'll call that forwards, or you can call it to the right or up. It doesn't really matter. It's all arbitrary. Then determine the acceleration between 10 seconds and 12 seconds. So here we want to know what that acceleration is. It's the gradient. So it's the final take the initial velocity, or v take v naught. It's all the same thing. We divide it by the time it took, and we get our acceleration. And it should be a negative acceleration, because even though, yes, we are speeding up, we are moving in a negative direction. So this represents an acceleration in the negative direction. Just like we say gravity is 9.8 meters per second, but that's not slowing you down, that's just speeding you up downwards. So negative for down in this case. Alright, so that concludes our lesson on graphing motion. If you look on the OneNote page, you'll see that there are some questions here to have a go at. So page 23 to 6, page 37 to 10 gives you distance time and velocity time graphs to have a go at. If you finish these in this lesson, have a go at some of the questions from earlier if you haven't already finished those equations of motion questions. And then from that point, you're done. Next lesson, we're going to start talking about prac writing skills, about how to graph with Excel, and really fine tune that prac report before we start the deconstruct in the following lesson.
Bye, have a beautiful time.